Welcome students to this another session on industrial metallurgy. This is session number 19 and is going to be a short session. Here in this session, I'll try to explain as to how has the inverse lever rule been working for us. Means you applied the formula in the last session that percentage of one of the phases is A by L into 100, the percentage of the other phase is B by L into 100. But what is the basis of the origin of this rule, the inverse lever rule, that we'll try to figure out in this particular session. And here I wish to bring to your notice that inverse lever rule is nothing. It's a this rule has come from the law of conservation of mass only. So let's again take an example to find out that see, in the last session we had discussed that what type of information can be obtained from a from an equilibrium diagram, and it was said that for any temperature composition given for a material system, we can obtain what number and type of phases, what are present in the material system, what is the chemical composition of the existing phases, and finally what is the relative amount of each phase. Now, if there are exactly two phases present in a materials system, then to find out their chemical composition, the tie line concept is used. And similarly, if exactly two phases are present in that material system, the lever rule can be used in order to determine the relative weight of each of the existing phases. So let's assume that we have been given an alloy of composition 65% copper and 35% nickel, and this alloy is present at some temperature that it lies in the two phase region. So you can see that the temperature composition point comes out to be Q, right? This should have been mentioned as TZ. So the temperature composition point for TZ and 35% nickel composition comes out to be Q. We observe that the material system is lying in a two-phase region. The two phases are a mixture of the liquid solution of copper and nickel and the solid solution of copper and nickel. So who gives the chemical composition of these two phases? Because exactly two phases are present, the line PR, that is the tie line, gives us the chemical composition of the two phases. The point P gives us the chemical composition of the liquid phase, and the point R gives us the chemical composition of the solid phase. Now, having found out that, now we are interested in finding out that if we have been given, say, 100 grams of the alloy, what weight or what mass of this alloy is because of the liquid solution phase, and what mass is because of the solid solution phase. Now, if we are directly applying the lever rule, we know that PQR is to be taken as a lever of length L. The fulcrum is at the temperature composition point Q. There are two arms, one is PQ and the other is QR. The compositions in terms of nickel are 28, 35, 40, which have been obviously picked up from here. 28 is for point P, 35 is the alloy that we have taken, and 40 is for point R. And these two arms lengths have been designated now by A. A would be 35 minus 28, that is 7, and B would be 40 minus 35, that is 5, and the length of the lever would be 40 minus 28, that's 12. That is exactly what has been written down by me over here. Now students, this is inverse lever rule. So what is the amount of the liquid phase? Amount of the liquid phase, liquid happens to be on this side, so don't take this side of the arm, take this arm, and this arm QR is B, so B by L into 100, so that makes 5 by 12 into 100. So 41.67% weight of the alloy is because of the liquid phase. And what would be the amount of the solid phase? 100% minus 41.67%, that comes out to 58.33%. Alternatively, if we have to find out the amount of solid phase through the inverse lever rule only, the formula would be amount of solid phase here, it should be A. It should be A by L into 100, and that would be 7 by 12 into 100, which again comes out to be 58.33. But now we some of you would be wondering that how directly this formula B by L, or this should have been A by L into 100, has come. So as I said a while ago, that these have come from the law of conservation of mass. And now let us see how. So let us assume that so we are not now directly finding out the amount of the liquid phase and solid phase directly through the inverse lever rule. Rather, we are going to use the law of conservation of mass to make these calculations, and in the end you will realize that the way we have been calculating, we come up using the inverse lever rule only. So the alloy is of composition this, and is present at temperature Tz. There are two phases, liquid and solid, present in it. Now suppose the total mass of the alloy that you have taken is 100 grams. Now because 100 grams of the alloy has been taken and its composition is this, that means this alloy is containing 65 grams copper and remaining 35 grams nickel. Okay, now because it's lying in a two-phase region, using the tie line, you can find out the chemical composition of the liquid phase and also chemical composition of the solid phase. Now let us assume that the total amount of solid phase present in the alloy is W grams. So suppose the solid phase is W grams, we have taken 100 grams of the alloy. So what would be the amount of the liquid phase? The amount of the liquid phase would be 100 minus W grams. So now what we'll do is, we have with us alloy 100 grams of composition this, and in this solid phase is being assumed to be W. Now let us see what amount of copper and what amount of nickel go into the solid phase. So the solid phase is W grams. Okay, now in this solid phase, if the chemical composition of the solid phase, okay, let me again show to you chemical composition of solid phase. Chemical composition of the solid phase is 60% copper and 40% nickel, and weight of the solid phase is W grams. Sorry, mass of the solid phase is, so what does that mean? That means that if total amount of solid phase is W and its composition is 60% copper, 40% nickel, what is the weight of copper in the solid phase? 60% of W, so 0.6 W. What is the weight of nickel in copper in the solid phase? 40% of W, that is 0.4 W. That is what we have done on the next slide. So what is the amount of copper in solid phase? 0.6 of W. And what's the amount of copper in liquid phase? 0.72, 0.4 of a W. And similarly, if I start doing analysis of the liquid phase amount is 100 minus W. And what's the chemical composition of the liquid phase? Chemical composition of the liquid phase is 72 copper, 28% nickel. So what would be the amount of copper in the liquid phase? The weight of the mass of liquid phase is 100 minus W. Chemical composition is 72% copper. So what's the weight of copper in the liquid phase? 72% of what? 72% of 100 minus W. So what's the weight of copper in the solid phase? 0.6 of W. What's the weight of copper in the liquid phase? 0.72 of 100 minus W. And this is the total amount of copper in the alloy which has gone into solid and liquid phase. And what's the weight of copper in the alloy? It's 65 grams. So what I've done right now, 0.6 of W and 0.72 of 100 minus W is equal to 65. So if I equate like that, 0.6 of W plus 0.72 of 100 minus W is 65. If I rearrange the terms in this equation, I will see W is 72 minus 65 over 72 minus 60 into 100. And what's this 72 minus 65? Students, this 72 minus 65, or in terms of nickel composition, this would be 72 minus 65. Okay, so this comes out to be 7 by 12 into 100. So what is this 7? This 7 is this A by L into 100, the weight of the solid phase, and that's the same the formula that we have used as the inverse lever rule for finding out the weight of the solid phase. Similarly, if I would have done it for nickel, then the weight of the nickel would have come out, and if I would have done it for the weight of the liquid phase, here I have done it for weight of the solid phase. Had I done it for weight of the liquid phase, this would have come out to be 5 by 12 into 100, which meant B by L into 100. So I had proceeded starting from the law of conservation of mass, and I have come at this end step where I have got the direct formula, and that direct formula is nothing but the inverse lever rule. So I hope you have understood the concept of inverse lever rule and how did we arrive at that final formula that we have used. So please mind it, the tie line concept and the lever rule concept. Tie line concept is for finding out the chemical composition of the existing phases. Lever rule concept is used for finding out the relative weight of the existing phases. But both these concepts can be used when under some composition and temperature conditions, there are exactly two phases present in your alloy system. If there are phases other than two, you cannot apply either of these concepts. So thanks for watching.